Hello, everybody. Thanks for joining me. I am Luca. I work at Elastic as a software developer within the ElasticSearch team. And today, I would like to talk to you about a new feature that is coming out with ElasticSearch 5.0. The first alpha version of ElasticSearch 5.0 is already out. It was released the 5th of April. But before I get started, let me ask you a question. How many of you know what Elasticsearch is? Can you raise your hand? Good, good, good. How many of you are using it already? Okay, a bit less, but that's good, that's good. Okay, I was just double checking that my assumption is right, because the talk is not really a beginner talk for Elasticsearch. The assumption is that you pretty much already know what Elasticsearch is, and we're not going to focus on what the product is and what it does, but more on a new feature that is coming. So we'll focus on that. Uh-oh. The battery left me already? That's new. Okay. So what are we going to see in this talk? First of all, we're going to try and figure out why we actually decided in the beginning to work on this new feature and how it works internally. We will see a few examples of the APIs and how to use it. And we'll also see which APIs in Elasticsearch support the Ingest Node. And at the end of the talk, we'll see we'll play around with the APIs practically, and I'll show you a little bit of demo. So let's address first the question, why Ingest Node? Why did we need it? Why should you use it at all? And it can be all summarized through this very simple question, which is more of a requirement. I just want to tail a file. It's a simple requirement. You have a file. It can be logs, but not just logs, just a file. And you want to send it somewhere, to Elasticsearch. You want to make it searchable. You want to be able to search against it. The answer to this question, the solution, would be to use Logstash, pre-node ingest, which is a great product. And it's very, very, very flexible. By the way, how many of you are familiar with Logstash? Can you raise your hand? Good, good, good. OK. So Logstash supports multiple inputs, which is where data comes from. In this case, it will be just a file. Very simple. It supports a chain of filters, which is what we're going to use to enrich our documents. And at the end of the chain of filters, we will have an output. That is where we want to index our data, where we want to send it to. And that's great. The nice thing about Logstash is that it supports multiple inputs, multiple outputs, not just Elasticsearch, which we have here in the example. And it can also pull data from a lot of different systems. It supports a lot of plugins, and the community has been great there. What is the problem then with it? It's not really a problem with Logstash itself. It's more with our use case, which is very simple. And this is not a very simple solution. We weren't that happy about it, because the setup that we would require in this case would be to have a server where you have some lightweight agent that is able to capture the logs, the file, and send it somewhere else, maybe to a message queue, or maybe directly to Logstash, which has to be on another server. It can potentially be where the files are, but maybe it's better to have it separately. And then Logstash on this server would need to be running our filters, enrich our documents, and then send them somewhere else to Elasticsearch. It's not that complicated yet. We just want to tail a file. If we go back to our requirement, this is not a very simple solution for this problem. You can still use Logstash for complex use cases if you want to do a lot of enrichment, and if you have a very complex system, but still, with a simple use case like tailing a file, we didn't have a good solution for it. And the solution is now the Ingest Node, which is we just have lightweight agent, which is called FileBit, which is able to gather data from a file, send it somewhere directly to Elasticsearch, so no Logstash in between. What was the problem with this solution before we had Ingest Node? The problem was that FileBit is able to collect data from files, but it can only turn a line of this file, which is tailing from, to a message, which is a JSON document. It cannot do any enrichment, right? It can only forward it somewhere. That's what it does. FileBit, collect, and ship. That's it. And then this message goes to Elasticsearch directly. And we need to have there a component that is able to actually enrich our documents and do something with them, not just index them and store them, which is pretty much the job that Logstash would do before sending the document over to Elasticsearch. And you can see here in this slide the result of the ingest processing. We have a single field message, which becomes multiple fields extracted out of that single field. So we have now the HTTP verb, the timestamp, we can make sense of it, and a lot of other things that are extracted out of it. So hopefully we now know why we went ahead and developed this feature and why we should use it. But how does it work, really? This feature is very, very similar to Logstash, right? We still have a pipeline. We just call it a pipeline instead of filters, and it's composed of a set of processors. The processors are very similar to Logstash filters, but we cannot configure anymore like multiple inputs and multiple outputs. The input is what gets within Elasticsearch, and the output is just what we want to index within Elasticsearch. So we do lose some flexibility there because we are already within Elasticsearch, but we still have the chain of filters, which we call now processors. How do we define a pipeline? This is an API that's storing a pipeline within Elasticsearch. It's just composed of a set of processors that will be executed in order. And if you are already familiar with Logstash, you may be familiar already with also some of the processors that we have that we'll go through later. So every processor has a name and some options that it can support, depending on the different processor. Once we define the pipeline, we can finally refer to it through, for example, the index API. We are now indexing the document. We are actually sending the document. This is what FileBit would do. It's using the index API in Elasticsearch. It's sending over a document which has this single field message, and it's providing a pipeline ID, which is the new bit in this API. Not just indexing the document, but also referring to a pipeline and saying, I want to index this document, but I want it to be enriched before it gets indexed. Then we go, retrieve the pipeline, we execute it, and then we index the document enriched finally. And once we index this document, what we actually get back from the system, what gets into the system is this enriched document with many more fields, which is what we already saw in the beginning. So the enrichment has happened, and that's what we have in the search engine. Along with the put pipeline API that we saw, we also have other APIs to do just CRUD with pipelines. So we already saw the put for the pipelines, which allows you to not only create, but also update an existing pipeline if you provide it with the same ID. Get by ID for a pipeline. Get also supports wildcards. So it can return multiple pipelines at the same time with a single request, and delete by ID. So that's pretty simple. Now that we know how to use pipelines and how to interact with them, let's have a look at what are the processors that we can use within a pipeline that we can use to enrich our documents. And this is something that we've been working on still. So this is the set of processors that we have. We'll go through each of them now. And some others may be developed very soon and may be out soon. But this is the set where we have for now. It is not a one-one from Logstash. So it's just the main set of filters that we found were useful, and we ported them to Elasticsearch. The first one is Grok. For any of you that are familiar with Logstash, Grok is the first thing that you look at. Grok allows you to extract multiple fields out of a single line of log, right? So you configure multiple patterns, like where the date should be found, where the HTTP verb should be found, and so on, and you're able to have multiple fields out of it. Once you have all of the different fields, you can also apply other changes to your documents. And mutate is just a set of processors within ingest. For example, you can set a field, you can remove one, you can rename a field, do very simple things like converting the type as well, playing around with strings, and so on, or also with the arrays. So these are all simple things. What you also may need to do is playing around with dates. You are able, with the Grok processor, to extract the date out of the single log line. But the format of the date may vary depending on the log format. And you want to unify that. So you would use the date processor for that. You specify a pattern, where to take the date from, and the output of that will be a unified date that can be indexed within Elasticsearch. GeoIP is another type of enrichment that we can run. If we have an IP field taken from the log, we can go, take it, it's just a string, and we can use it as a lookup and do a lookup in a local database that gives us a lot of geographical information about the location of that IP address. And then all that information can be indexed within the document itself as a new field, which is going to be an object. For each Well, you have lists. You want to do the same thing with all of the elements in a list. And that's something that you can do with the for each processor. Or you can make things fail, which may sound weird, but it may be useful as well. Let's say that you want to provide a custom message when things fail or make them fail explicitly, and you have a fail processor for that as well. And this ties a bit to what I'm going to explain you about later when it comes to handling failures. We will see that. And last but not least, also plugins. There is a new Java interface, which is called Processor within the ElasticSearch core. You can go implement it and plug it in as a plugin within Elasticsearch. So you have your own processors, if the ones that comes out with Elasticsearch are not enough for you, or if you have custom needs. All that said, I briefly mentioned that we can do things when it comes to failures. And let's have a look at what happens when something goes wrong, because things will always go wrong, right? We have some input that comes from a log line or from a file, and something's going to be broken there at some point. In this example, I have broken the time zone in this log, so the date will not parse correctly. So the Grok processor will be able to extract all of the different fields, and it will call that field timestamp, but the date processor, which is the second in the pipeline, will say, no, this is not the date, I cannot parse it. What happens by default if I send this message through this pipeline? What happens is that the Grok processor works perfectly. The date processor gets this date, it tries to parse it, and it throws an error. So the client will get back an error directly, 400 bad request, with a message that will say, unable to parse date, can't do anything with it. So as a result, no document will be indexed. We just get back an error. We have to fix it. Okay? That's the default behavior. We can go and change, though, this behavior. We can, for example, declare a onFailure element within the pipeline, at the pipeline level, which means if anything goes wrong within this pipeline, this is what you should do. And what you should do is expressed in form of a set of processors again. In this example, we only have a set processor, which, for example, what could it do? It could forward the document to a different index called failures. Then afterwards, we can have a look at the failures and have a look at why things failed, maybe go fix them, or reindex those documents, whatever. It really depends on the application and the type of data that you get. But this is, again, a very generic type of failures. We don't know exactly what went wrong. It's just a catch for the whole pipeline. So what happens if we go ahead and send again this document through this pipeline is that, again, the Grok processor will work. The date processor will say, I cannot parse this. But then it doesn't fail. It will go through the onFailure element. It will read those processors, and it will execute them. So let's say we decided to change the index name of those documents and send them to another index. That's what will happen. And most importantly, we will be indexing that document. So things won't fail. The application won't get back an error in that case. Which is kind of nice. And if you're familiar with Logstash, this is something that the Grok filter does, for example. It marks Grok parse failure a lot of things when things go wrong, and it will still index them somewhere. But in this case, we're very flexible. We allow you to configure what you want to be happening when something goes wrong. That said, again, we are talking about generic failures handling. We can do something a bit more specific, like say, because I know that the date processor is likely to fail, there can be problems within a date, for example, more than with other things. We declare some onFailure element specifically for that processor. So we say onFailure, only for this processor, go execute another set of processors. And you can nest these things. So for example, within the onFailure, you can again declare another onFailure. So you can really go nuts there. And the idea would be then that if I send again this document, I could say, okay, because I know that the date is broken, I want to remove that date. I don't know what to do with it. And maybe set another date or set another field. Whatever. It really depends on your business logic and what you want to do with that specific failure. What's important to note here, though, is that after the onFailure for that processor has been executed, we go back to the following processor in the original pipeline. So we don't return directly from the set in the on failure to oh, OK, but we go back to the pipeline, and we execute the remove processor that was there in the beginning. While in the previous example, with the on failure in the pipeline, we wouldn't. If you don't get this, don't worry, I'm going to demo it. So we're going to look at JSON and play around with it so that it's more clear. But that's how we can handle failures. So a lot of flexibility there. We get back to this. One more thing that I would like to cover is how Ingest Node works internally. When it comes to nodes and where requests go. And the first case is the default scenario. If you're familiar with ElasticSearch, you may know that ElasticSearch nodes have roles, or you can assign them node types, let's say. You can say this node holds data, but it's not master eligible. And with node ingest, we introduced a new node type, which is called ingest. So you can disable that feature. By default, all of the roles are enabled. So that means you start a node, it's going to be able to hold data, it's going to be master eligible, and it's going to be able to run ingest pipelines. So we just start 3 nodes in the same cluster, and we have an index with 3 shards and 1 replica each. And we are a client that's going to send requests. Oh, by the way, the CS part in the slide is the cluster state. The cluster state is where a lot of information about the cluster are stored, like what nodes are part of the cluster, what indices are in the cluster, where are the shards for those indices, a lot of information. And surprisingly, that's where we store pipelines. So they don't go to an index, but they go to the cluster state. Why? Because when the client sends a request, the index request will refer to a pipeline that was stored. And the node that will be hit by this request will look at this request, and it will say, oh, there is a pipeline ID. Then I need to load this pipeline. The pipeline will be loaded from the cluster state. The cluster state is in memory already on all of the nodes, so that's very performant. We don't have to go and have a get or some other call that could be a performance bottleneck. So we just load from the cluster state, and the important bit in this slide is that whichever node we hit with this request is the node that is going to run the ingest pipeline. Okay? That's what we call the coordinating node. So first step, the client sends the index request. It has a pipeline ID. Node 3, which is hit by the request, will load the pipeline. It will execute, and it will enrich the document. At that point, we have to look at where the document actually needs to go. And that depends on the ID of the document. Let's say that this document is supposed to go to shard 3. Then what happens is that the document gets rerouted. The enriched document, though, gets rerouted to the node that holds the primary shard. And then, normal indexing operation. If you're familiar with ElasticSearch, this is nothing new. We go to the replica, and we do what we have to do. And then the document is finally indexed. And this is the default scenario. But if we want to do things a bit more complicated, for example, you go in production and you use Ingest Node a lot, then you may want to do something a bit different. Like, you may want to declare some of the nodes that can hold data. They are all master eligible. But they cannot do ingest execution. They cannot execute pipelines. So you would just say node.ingest false in the node configuration. And then you have another set of nodes, which are the 2 nodes that we have new now, node 4 and node 5. Those nodes will be ingest dedicated nodes. So in their configuration, you would say node data false, node master false, because they are not master eligible. They cannot hold data. And they will be there only to run ingest pipelines. That's the only thing they will do, apart from coordinating requests if you send requests to them. So in this example, let's go back to our request. It's the same request to the same client. We hit the same node, which is node 3. And then depending on which node we hit here, something different will happen. This node will open up the request. It will find a pipeline ID. And it will figure out that it cannot execute the ingest part of the request, which needs to be executed pre-indexing, right? So it will say, OK, I need to forward this request to a node that can actually execute the ingestion part. Then it will just reroute the request to a node that is able to do that. And it will round robin through the different ingest nodes that are available within the cluster. What would have happened if the client had hit node 4 or node 5, the pipeline would have been executed directly there. We got lucky. But if we hit another node that is not able to run ingest pipelines, the request is going to be forwarded to a node that can do that. At that point, the pipeline will be executed on node 5. Again, we load the pipeline from the cluster state, we execute it, and we enrich the document. And again, indexing. It's what we already know if we're using Elasticsearch. The document, which is enriched now, goes to the node that holds the primary shard for it, and then it gets replicated to the node that holds the replica. We have only one replica, so it happens only once. And this is pretty much what I wanted to explain about different nodes. So this is something that you want to take into account. Start simple if you want to use the ingest node. Start simple, you don't have to declare dedicated ingest nodes and so on. But if you go a bit more serious, you go into production, you may want to balance the load. Like say I have ingest dedicated nodes where all of the ingest processing happens, because it's very different from data-intensive operation that would happen on a data node, for example, like not only indexing, but also aggregations. So it's nice to balance the load that way. Last but not least, we do know now how to use the ingest node. We know that we have to declare a pipeline and we have to provide the pipeline ID, but where can we actually provide this pipeline ID? Where can we make use of this new feature? And I showed you the index API, which is one case. We are indexing a single document, a single message, and we have this pipeline ID. But the same can be done through the bulk API, of course. The bulk API is the API that is used to index multiple documents with a single request. Don't look too much at the JSON there because it's quite awful, but it's something that hopefully your client will hide, so no worries. The takeaway from that slide is that we support a different pipeline ID per item in a bulk API. So you're indexing multiple documents. Every document can go potentially to a different pipeline. That's it. And the third API that supports this is the reindex API, which is a very, very new API that got released in Elasticsearch 2.3. It's going to be part of 5.0 as well. The point of the reindex API is to allow you to get data from an existing index and reindex it somewhere else on another index. And we did have the tools before the reindex API was there, but it was a bit cumbersome to do. Because we would have to use the search API, but using a specific search type, which is scan, scroll over all the documents, and while scrolling, we would have to index those documents somewhere else through the bulk API. So now we have a single API. You don't have to worry about all of these things. You just call the reindex API. You specify the index where you want to take your data from. You can specify a query or the type. So for example, you can filter out some of the documents and take only a subset of the documents that you want to reindex. And then you specify the destination index, in this case, Apache logs. And again, you can specify there a pipeline ID. So say, I do want to reindex documents. I also want to enrich them while I reindex them. Now, the reindex API is useful because the more the development goes on with Lucene, the more you're going to need to reindex probably at some point to make use of all of the new features that come out with Lucene and Elasticsearch, especially the recent versions. There are also things that you cannot do at all without reindexing. Like, for example, if you're familiar with Elasticsearch, you already know probably, you cannot change an analyzer on an existing field. Or you want to make some no backwards compatible changes to your mapping. Then you need to reindex. And this is the API to actually reindex stuff from Elasticsearch itself. Doesn't mean that you have to use Elasticsearch as a source. You can also use your database and do it externally. But if you do have all your data within Elasticsearch, that's the way to go. And again, it supports a pipeline ID, so you can also make changes to your documents. There's also another way with the reindex API to make changes, which is you can provide a script. So there you have, it depends a bit on whether you prefer scripts, whether you prefer the ingest node. They may be able to do the same thing. There are things that you can do with scripts that you cannot do with ingest at this point, because of course with scripts you can do everything really. There are also things that you can do with ingest node, like GOP enrichment, that you cannot really do easily with a script. So up to you the decision. But both are supported by the reindex API. That said, let's see. I'll head over to my computer and let's have a look at a bit of demo that I prepared. First things first. How we start Elasticsearch? It is Elasticsearch 5.0, Alpha 1. So this was released the 5th of April. So it's not a snapshot on my machine. It's just some public thing that was released. And I have another tab with Kibana. Now, I must say that Kibana here is indeed a snapshot. It's not a released version yet, because Alpha 1 didn't have all the features that I needed for this demo. But it's a public snapshot. It's not like a fork in my laptop. The reason why I need Kibana snapshot is that Alpha 1 doesn't have the console yet. And this is kind of the way we bundle Sense, if you're familiar with it. It's just a console that allows you to send JSON requests to Elasticsearch and see the output. And it has a lot of auto-completion and suggestions. So it helps you a lot there. And the console tab that I'm showing you now is not available in Alpha 1, but it will be available in Alpha 2. Let me also ask you another question. How many of you are using Elasticsearch 1.x? OK, I won't ask 090. 2.x? Good. 3.x? OK, that was a joke. So I just wanted to verify that, that there was a big announcement at ElasticCon in San Francisco about the fact that we won't have a 3.0 version, not even a 4.0 version, but we will move directly from 2.3 to 5.0. The reason for that is that we want to align all of the versioning throughout the Elastic stack. So we just pick the highest version of all of the products. And the next major version will be 5.0. So that's why I'm talking about 5.0 and 2.3, which seems like years apart, but they are not. Okay? 2.3 was released probably a month ago, and 5.0 Alpha 1 was released only a few weeks ago. Now, back to Kibana. I won't show you any nice chart out of Kibana. Sorry about that. I will just show you JSON requests and JSON responses, but I guess that we're all developers pretty much, and we're going to be able to understand what's happening. There is going to be in Kibana, though, a new tab, which is going to be called the Add Data UI. The Add Data UI is going to be a wizard that allows you to add data through the ingest pipelines. So very nice. You won't see JSON there if you don't like it. You can just upload a file and get suggestions about all of the processors that you can use and be able to do that. It's not part of the demo, though, because it's not ready. It's being worked on as we speak. And the target is Alpha 2 for that. So it's going to be available pretty soon. The one bit that I'm going to show you in this demo is an API that I haven't talked about yet, which is the Simulate API. The Simulate API is very similar to the Analyze API in Elasticsearch. It allows you to simulate what would happen if I sent a document or a set of documents through a specific pipeline, okay? Without indexing any document, nor storing any pipeline. So just no data modification at all. The endpoint looks like this, _ingest, pipeline _simulate, and the content is going to be a pipeline that we define. Our pipeline is going to hold a set of processors. And also we declare a set of documents. Let's see how many typos I'm going to make here. The message is going to be very, very simple. Sorry, the document is going to be very, very simple. Just a simple field called message with a log line in it, which I'm, of course, going to copy-paste from somewhere. Then I need to make sure that I escape the double quotes. And let's try and create the pipeline that I showed you in the slide before with those three simple processors. Actually, because I don't want to make too many typos, I'm going to copy-paste this part. Let's see if it works or if it doesn't. Good. What have I done wrong? So the docs need to be wrapped under a source field. Why is that? Because you can also specify along with it some other metadata fields that are not really part of the document. Like, for example, the index. What have I done wrong this time? Oh, thanks. Yeah, these things happen. Alrighty. So the idea here is we didn't index any document, we didn't store any pipeline. We just have a simple pipeline that we specify on the fly with the Simulate API. It's composed of a Grok processor that will take the message field out of the document, and it will use a common pattern that is already defined. So I really didn't have to play around with the regular expression and patterns. I just went and looked at all of the patterns that are available. Those are the same in Logstash, so no changes there at all. We just know that an Apache log, a common Apache log, has this name, and I don't have to do anything more. And this is the processor that is able to extract all of these different fields from the message field. So we have a request and all of different portions. After that, we want to make sense of the date. So we take from the field timestamp, and we parse using this pattern, and we create a new timestamp field, which is the @timestamp field that we see here. We still have the original timestamp, which is in the Apache format, but we have a new one, which is in the Elasticsearch format, let's say the unified format that we're going to have for all of our logs if we have different formats. After this processor, we have a remove one that just allows us to get rid of the original message, because in the end, we don't want to keep it. We could have kept it. Depends on what you need. So at this point, we do see the final result, which is nice. We also see the index that I had specified here, while ID and type are just defaults for this API. But we probably would like to have some more information about all of the different steps, because we would like to know what happens after each processor. And the way we could find it out is by adding the verbose flag. Then the output changes quite a bit. We have a processor results element, which is an array, and each element contains the output of a processor. Okay? So the first one is going to be the output of the first processor, the Grok one. You see that we still have the message field. We still have a single date. We don't have the @timestamp yet. And we have a lot of different fields that are created by the Grok processor. Next one, we have the enrichments made by the second processor, the date one. And we do have the @timestamp field. Next one again, the message field is gone because the remove processor removed it. Let's add a few more processors to this. For example, we have response code and bytes, which are numbers, but Grok will extract them as strings. So it's okay, we will index them as strings, but maybe we want to be able to run range queries, for example, against them. And then we will need to index them as numbers. Then what we would do is use the convert processor for that. So the field is called response, and we say type integer. And now, at the end, we will have another output with the response code, which became an integer now, and so on. So this is a very nice API. That's perfect for a demo, actually, and to show incrementally what happens. So this is the process that you would go through when using the ingest node and trying to debug the pipeline that you would need, depending on your data. You can also specify more documents here, like you have different log formats, and you want to debug what happens with all of them. You can add them here to the array. Let's go ahead and add a new convert for the bytes one. And if we go to the bottom here, we see that bytes became a number. Now, the problem now at this point is that we have 5 processors. It's not many, but it may become a bit hard to associate which processor did what, right? Because we just have an array of results with a document. And we don't really associate yet which output belongs to which processor. We could, for example, report the whole content of the processor together with the result in the response. But we decided for now not to do it. But what you could do instead is associate a tag with the processor, which is just for debugging purposes. So you do tag, and you call it convert response, for example. And you do the same with bytes. Then if we go down, we see, okay, now we are sure that this is the output of the convert response processor, right? We can associate the output with what we had in the simulate API, and the same with convert bytes. So that's a nice addition as well. To go back to what I said in the slide about on failure, things go wrong all the time, right? Let's say that the log line is broken. I break the year, and I make it so that it's not parsable. Let's see what happens. And this is very nice because you can debug it actually before it happens on production. So if this happened with the default behavior, as I showed you before in the slides, something would break. This is what you would get back. We don't have here the HTTP code that you will get back, but I can tell you it's for bad request. And this is because the grok processor broke. While, for example, if you break the time zone, which is a bit more subtle, the grok processor is able to extract the date because it doesn't really know that it's not a date, and the date processor will break. Then what happens is that the first processor will say, okay, executed. We have a lot of different fields created out of it. The second one will say, no, this is not a date. I can't go ahead. And this is the one that I showed you in the example before, in the slide. So then, what we could do here is say, because we know that some of our dates can be broken for some reason, we can handle this failure. And we can go here and say, no, actually, I want to do something at the pipeline level before, because it's better. So we go down to the pipeline, within the pipeline object, after the processor's element, and we say, on failure. And this is, again, an array that holds a list of objects, which are just the processors that we want to execute in case there is any failure in the pipeline. And let's do what I mentioned before. For example, let's move those documents to a different index. So we declare, again, the set processor, which we are now familiar with, and we say field. And in this case, we are referring to a metadata field. It's not really part of our documents. It's something that we specified in the URL when indexing the document. So we specify index type ID and the pipeline ID as a query string parameter. We can still modify the index that the documents go through using this metadata field. And we declare a value for it, which can be, for example, something static. Now, let's have a look if on failures worked. The first processor, grok, worked. The second one broke, which is fine. But after the second one, we still have something, which means that we go ahead with the execution of the pipeline. In this case, we read from the onFailure handling in the pipeline, and we changed the index of the document. After that, we don't have anything. So this is the document that actually gets indexed after processing this pipeline. Still, we have something broken in the message, but it gets indexed, and we mark the failure. There's more things that we can do with marking failures. For example, something that I haven't mentioned yet is another portion that we have in the Simulate API. That is ingest metadata. It's something that's in the context of the execution of the pipeline while the document is there, and it goes away as soon as the enrichment has happened and is completed. So those fields don't go anywhere, don't go really within the document itself, unless you do something with them. Let's see what we can do, for example. We see here that we have, because something failed, we have the message of the failure. We have the tag of the processor that failed, which we didn't set in this case. And we have also which processor failed. If we add to the onFailure at the pipeline level a new processor here, and we set a field failure, but the value in this case is going to be an object, which is supported. It doesn't have to be just strings or integer, right? We can just put in here a whole object and say message. And one more goodness, we can specify templates. So it's not really scripting, it's just to refer to field values that are around in the context. And in this case, we do this, _ingest dot onFailure message. Let's see what happens. We go to the bottom again, and we see that there is a processor that changed the failed index. Actually, let's give it a tag, which is better, so we can track it down. This is something that you can do with any processor, and call it mark failure. So we go to the bottom, and we see that the last processor that executed was mark failure, and we have a new object in the document that contains the message of the failure. So if we don't do anything with that ingest metadata that we have in the context of the processing, it doesn't go anywhere. But we can mark failures, we can make documents go to another index, and we can also say index the text of the failure. Or we can also add here the processor that failed, the name of the processor. Which is called a failure processor type. And we have an object now, and if we had sent this document through this pipeline, we would have had a new document within the failed index that contains a failure that we can look at and reason about it. Maybe go fix it, maybe go fix the documents, maybe do something in the pipeline, but we can incrementally fix things. This is, again, very generic because it's applied at the pipeline level. So we can't really reason about a specific error, like the date broke, but also grok can break. Every processor can break. If we know that we have some processor that is most likely to fail, we can go and declare on failure for that processor specifically. And that's what we do now. So we go within the date processor, and we say on failure. Again, it's an array of objects, and every object is going to be a new processor. What can we do here? We can, for example, set some default date. I'm just saying, but maybe it's not the correct thing. Depends really on business logic and what you want to do. Field could be just at timestamp. A timestamp would be the field that we are missing when the date cannot be parsed to a date, right? Because it's the new field that has timestamp that is not going to be added if the date processor breaks. If we go back and look, grok created a timestamp field in the Apache log format. We want to add an at timestamp field in a different format. That's the part that fails. So we set that field directly to some value. Some value could be, again, something that we have along with our ingest metadata, like the ingest timestamp. So if we go now, let's again tag the processor so that we don't mess it up. Set default date. Again, the date processor broke, which is great. But now we are executing this specific processor that will be run only if the date processor breaks. And what it does is it sets some default date to the at timestamp field. That default is just the timestamp of ingestion, so when the document came to the ingest pipeline. Maybe it's not a good idea to replace your original timestamp coming from the logs with this one, but it's just an example. It's something that you can do. So you always have within your ingest metadata this information. If we look at the first output here, we see that we don't have failures because nothing failed, but we still have the timestamp, and that doesn't change, of course. It's when the ingest pipeline started for that specific document. One more thing that we could do, for example, would be to set some default for the bytes. Let's fix the time zone here so that everything goes well. Let's go to the bottom to verify that everything goes well, yes. And let's say that the number of bytes is a dash, which is something that may happen with Apache, instead of a number. Now, what happens by default? Well, by default, with what we have defined up until now is convert response works, convert bytes breaks, of course, because it's not a number. And then the on failure at the pipeline level kicks in. So again, we wouldn't have rejected this message. We would have indexed it under failures. But maybe, because we know that this is a recurring error, we can handle it differently and say, go to that specific processor. And again, it's the same thing as before. Declare summon failure. And what we could do here, again, set some default. It really depends on what you need. For example, you could say bytes. -1. That looks like a nice default. Maybe 0. Depends on what you want to do. So we go down now, and we see that we do have a failure for the convert bytes processor, but it's on failure kicked in, and we have bytes set to -1. So I guess you get that you can play around with on failure, and that's a very good tool, and especially because it allows you to make decisions about what you want to do with failures when something goes wrong. Back to the presentation. This is pretty much the conclusion. Go get ElasticSearch 5.0 Alpha 1. It's already out. Alpha 2 is going to come very soon. After Alpha 2, there's going to be probably a beta. So it's going to take a while to get to GA, but we are close. Please go get it. And I have stickers here if you want to come down to get some. And don't forget to vote the talk. And thank you. And of course, open for questions. So if you have any.
Well, as you said, go get grab 5.0. When is it advisable to use it on your production stack?
When it's generally available. It's not even beta yet. So now, even if you read the release blog, it's alpha. So please go grab it, but please don't install it in production. You're going to hurt yourself. I mean, it does work, but yeah, it's not production safe yet.
But when you guys have Elastic claim, okay, it's production ready, when is it advisable for the large production stack to increase
Okay, let me repeat the question because you don't have a mic and I forgot about that. So the question is about upgrading ElasticSearch and when GA is available and when is advisable for people to upgrade to the new major version. I would say whenever generally available is out. It's safe, it's well tested already. The alpha version is well tested. The main reason why we have an alpha is that we want to get it out there to have people test it, and between the different alpha versions and between alpha and beta, there won't be any guarantees with backwards compatibility. We can break, APIs, we can break the data format, and so on. Once we have beta out, it's safer to install, but not in production yet. Once we have GA, we will care about backwards compatibility, which is your concern, right? Because you don't want to install it in production and then needing to reindex or do crazy things with your data. That's the main point. Yeah.
So people using ElasticSearch 1.0 or 1.x, is there a migration scenario from 1.x to 5?
Okay, so the question is about migrating from 1.x to 5.0. There isn't a direct migration path. You have to go to 2.something at some point. So you have to step to each major version. To go to 2.0, though, we have a migration plugin that you can run in your cluster before you migrate. That's going to tell you what you may need to change before you go and upgrade. So like, because we made breaking changes, we changed things in the mappings and how things work internally. So it's going to advise you to change some things. Then you're ready to go live, you go to 2.0, and then you need to do the same thing again to go to 5.0. Yeah. From 2.3 to 5, yes, there is. Yeah, definitely, yes. Yes.
Is there an internal queuing mechanism inside the ingest feature or when you have dedicated ingest node?
Good point. So the question is about whether we have any queue within ElasticSearch to handle failures or things like that. No, we don't have any queue for now. We kept it very simple. So for now, the idea is I just want to tail a file, right? And let's get the queue and logstash out of the way for now. That doesn't mean that you don't need to use them, but to start simple, let's just use processing and no. We are going to see whether we can improve like the communication between FileBit or the Bits agents with an Elasticsearch node to see whether we can make it better, because it can happen that you lose events there, you lose messages if things go really wrong. And it's something that we've been working on. Yeah, we will improve for sure. Other questions? Good, thanks.